is intermolecular forces. And intermolecular forces help to explain what makes a solid versus what makes a liquid versus not having any in a gas. So we're going to look at our intermolecular forces today, and we're going to look at the different types of them, and we're going to get a definition of just what is that type of force. So as we look through these, we are going to think about a word that we had last semester, which was called an intramolecular force, I-N-T-R-A, molecular force. So if I have my little water molecule here again, with this water molecule that I have here, I have hydrogen sticking to oxygen, and I have another hydrogen sticking to oxygen. So with my oxygen sticking to my hydrogen here, that is an intramolecular force, an internal force holding together those different elements together because of their electrons that are there. Either they're shared or they are stolen. What we're going to talk about for this section is intermolecular forces, which are the forces that make water molecules stick to one another. So we have this water molecule being stuck to this one, being stuck to this one, or if we have a liquid, that's what makes them actually stick close to one another overall. So your intermolecular forces are what make something a solid, what makes something a liquid, or what makes something a gas. Now there's 3 different types of intermolecular forces that we're going to talk about. And with these 3 different types of intermolecular forces, they can either stick together the same molecule, like water sticks to water, which sticks to water, which then we have a big little glob of water molecules. Ooh, I'm losing my water, sorry. My water molecules all sticking together like this. Or maybe this is how your pen is sticking to your paper, or graphite in a pencil sticks to a paper. And I always talk about this in class, that if you're writing with a pencil, or even a pen, especially like a ballpoint pen, and you have lined paper, sometimes you're writing, and as you're writing, you get to a spot on your paper that no matter what you do, that pencil or that ballpoint pen doesn't stick. You can write above it, you can write below it, but for some reason in that one little spot, you can't actually write on the paper. Well, the reason why that happens is because you have cellulose, which comes from a tree, in the paper itself. And when that cellulose is not present in that particular part of the paper, the graphite from your pencil cannot actually adhere to the paper because there is no intermolecular forces that are available for that to happen, or the correct intermolecular forces for that to happen. So when we're looking at our intermolecular forces, they have to be the same molecule sticking together, like water sticks to water or graphite sticks to graphite, or they can be different, where like you have the graphite sticking to the cellulose that is actually in the paper itself. Now the 3 different types of intermolecular forces, you have hydrogen bonds, which isn't actually a bond per se, but it's called a hydrogen bond. Dipole-dipole. People read this and say dipole, but it's a dipole-dipole. And you have dispersion, which some people call London dispersion forces. So with these 3 different types of forces, 2 of them are relatively weak and 1 is super strong. We're going to talk about the weaker ones first. The first one is this dipole-dipole. If we remember back to first semester, the word dipole means polar. So when you read this, it's actually a polar force. So looking at this, the definition says a weak force that holds together polar molecules to one another. So when we have a molecule that's polar overall, which if we remember back to the nomenclature unit, if you have something that's polar, that means that they are not sharing their electrons equally with one another. One of them is more electronegative than another. So you have that weird pull of electrons being like pulled away from one and towards another one. You end up with a slight positive and negative force. Opposites attract, or they're going to stick together. So if we look at this, the H and the Cl, chlorine is a lot more electronegative than hydrogen. So with chlorine being a lot more electronegative than hydrogen, the electrons pull towards chlorine and you end up with a slight negative charge, a slight positive charge. Well, this one is doing the same thing, this positive and this negative, opposites attract, they stick together very weakly. Now it's easy to break these apart. Again, it's just kind of like a magnet. So these are water molecules. These aren't actually dipole-dipole, but with my little water molecules, all I have to do is just take them and move them, and they break apart very easily. Again, they're just magnets on these, but it's very easy to separate. If you have a pencil that you're writing on a piece of paper, it's very easy to separate it off the piece of paper with an eraser. So looking at these, the dipole-dipole forces are relatively weak. They are very easy to break, but these occur with polar molecules. Now, dispersion forces happen with nonpolar molecules. So nonpolar means that you're sharing your electrons equally with one another. When they share their electrons equally with one another, you have something like hydrogen or chlorine or bromine, all of those Brinkelhoff elements. Carbon dioxide is nonpolar due to its shape because it's linear, but it's pulling equally on each side. So when you have these nonpolar molecules, they are going to create these dispersion forces, which helps things to stick together. This little guy underneath my picture here, that's a crested gecko. Some of you guys might remember I used to work at the zoo. So little crested geckos are the ones that will stick to glass. And as they stick to glass, they can like climb up the glass. That's because of dispersion forces. If you have no clue what I'm talking about, I do have a video on the next slide. And this is a reptile society that's in a classroom. I'm going to be honest with you, the one little boy that is in this video, he's very excited about the crested gecko climbing up the different surfaces. But in this video, the reason why I'm showing it to you is the crested gecko itself can climb up some surfaces, but it can't climb up other surfaces. So he goes through and he shows you which ones he can climb and which ones he can't. Well, it should play. Okay, we're going to play it from here. Backup plan.
There we go. Saw that?
Maybe it's just more easier to use than
on the whiteboard. It's too slick. He's getting no traction. He can barely hold on at all. There. See? We got him. Okay.
Okay, so I'm going to pause it right here. So in this video so far, he was climbing up the one shelf. He jumped onto the guy. He was able to stick to his shirt. Put him on the whiteboard. He's not able to stick to the whiteboard. That is because it has a different type of force. So if he is nonpolar, maybe the board has dipole forces. Those two different types of forces don't allow him to stick together. So he can climb on some surfaces he can't.
Hey, okay, little gecko. Let's go find something else that you can climb on.
So we can see him.
Let's see. So he can hold on to the bulletin board. He's doing pretty good at that. Yeah. Okay, now we're going to go see what else he can climb on.
He's kind of sliding a little bit, though.
Well, let's see.
He's sliding, but he's still doing it. He's kind of sliding.
So those little tiny hairs on his toes with all those tiny little ends.
See, until he's kind of sliding.
They can hold on very well.
Until he's not like sliding, but still.
Yes, he's sliding a little bit.
But
now, if he wanted to, he could run up this really fast, and he wouldn't slide. See, he would just keep on going. He's pretending he's on a tree out in New Caledonia.
Make sure it don't. What about?
So let's put him on the glass.
No, she can't climb.
And let's see if he wants to climb the glass.
Like the fruit.
Well, I've seen him climb glass before, but it looks like today he doesn't want to. Come on, little guy.
Maybe it's too. Well, there he goes. He's doing it.
So he can do it if he wants to.
He just looks like he's still.
Look, he's going for the easy way. He's like, I'm going to climb up the sides. Yeah. Pretty cool, huh?
Okay, so the crested gecko was able to stick to some surfaces, but he was not able to stick to other ones because of the, he has a little setae on his feet. In the next slide, I have another video. I'm not going to play it in this video, but in case you're wondering what actually makes them, stick, this video is actually pretty informative on finding out why they can actually stick to some surfaces versus others. But it has to do with these dispersion forces. Because of the what makes up their toes basically, it creates these dispersion forces that he can stick to other things that are nonpolar, but he cannot stick to things that are polar because it is a different type of force that allows him to stick. Now, if you think back to the one where the kid kept saying he's sliding, that was paint. Paint is a mixture. So with paint being a mixture, maybe there is dispersion forces and dipole-dipole forces in that same mixture, which is why he's allowed to climb up part of it but not others. It could also be because of the texture of the paint as well. I'm not really sure in this case what the particular reason is. So the last type of bond that we have, or force that we have, is called a hydrogen bond. Hydrogen bonds are very strong in comparison to the other two, but they're both pretty weak. Hydrogen bonds is what makes water stick together. So if you want to separate water, take a drink, spit, turn on and off the sink. So you can break these bonds very easily. So it's not really like a chemical bond that we talked about. It's more like a hydrogen force, but it's called a hydrogen bond for some reason. But these hydrogen bonds are made up of the most electronegative forces that are there. So with your electronegative differences, you have hydrogen present and oxygen, or you have hydrogen and nitrogen, or you have hydrogen and fluorine. And with your different types of bonds that are present, if you have hydrogen and oxygen, hydrogen, nitrogen, hydrogen, and fluorine, any of those different things, you're going to create a hydrogen bond. And that's because they have such a strong electronegative difference that they create this different type of force that's actually there. Now, when I say that they are strong, like I said, they're pretty easy to break. All you have to do is take a drink of water. But in comparison to the other two, they are very strong, so they're kind of on a league of their own. Water is weird. You're going to hear me say that a lot through the next few units. Water is so weird, mainly because of these hydrogen bonds. Hydrogen is a covalent compound. It should not have as high of a melting point that it does. It should have as high of a boiling point. It shouldn't have a lot of the characteristics that it has because of these hydrogen bonds that are present. So when we're looking at your hydrogen bonds, they're kind of in a league of their own, and they are stronger intermolecular forces than the other two. Now, what you're going to have to do with these today is you're going to have to identify the type of intermolecular force that is there. You'll need the electronegativity values like we had last semester, so I'll have those on my screen here. And we will need to figure out, is it dispersion, or is it dipole-dipole, or is it a hydrogen bond, based off of what we said up top. Dipole-dipole are polar, dispersion forces, are nonpolar, and then hydrogen bonds have hydrogen and oxygen, hydrogen and nitrogen, or hydrogen and fluorine. So looking at this first one, I have hydrogen present. Hydrogen is bonded to fluorine. Because I have hydrogen and fluorine bonded together, that's a hydrogen bond. I don't have to look at my electronegativity values at all whatsoever on this one. It is just a hydrogen bond. Check, moving on. Now the next one is N2, that's nitrogen. With the next one being N2, nitrogen's electronegativity value's 3.04. When you draw this out, you just have nitrogen bonded to nitrogen. The difference between 3.04 and 3.04 is 0. So when we look at our electronegativity differences, we have anything that is under 0.4 is nonpolar. 0.4 up to 1.7 is polar. So because my electronegativity value on nitrogen is 0, this one is a nonpolar bond. So nitrogen is a dispersion force because it is nonpolar. Now I'm going to do the last one real quick. The last one, remember, hydrogen can never go in the center. Halogens can never go in the center. So I have carbon that is going to go into the middle. I have hydrogen, chlorine, chlorine, and chlorine. And I don't even need to really worry about drawing the rest of my stuff that is there. I'm just going to look at the general shape, which looks like this. With that general shape, remember we need to get a difference between chlorine and carbon. We're going to get a difference between carbon and hydrogen. If one of those differences is polar, the entire thing is polar. So we have a difference between carbon and hydrogen, and we need to find a difference between carbon and chlorine. So when I look at my chart up here, it says carbon is 2.55, hydrogen is 2.20. So I'm going to get a difference, between those two. I also need a difference between chlorine and carbon. So I'm going to do two separate math problems. When I do my two separate math problems, I'm going to get an answer here, figure out polar, nonpolar, get an answer here, polar, nonpolar. When I get those two different answers, if one of them is polar, the entire thing is polar. So pick up my calculator, get the difference between hydrogen and carbon, so 2.55 minus 2.20, I get an answer of 0.35. So with that answer of 0.35, that is nonpolar. Let me get the difference between the next one. 3.16 minus 2.55. On that one, I get an answer of 0.61. So that one makes it polar. Because I have something that is polar, the entire thing becomes polar. So that molecule is a dipole-dipole intermolecular force. Dipole-dipole is my answer because it is polar. Now on the next one, I have carbon with two sulfurs. With my carbon with my two sulfurs, if I drew this one out, you're going to end up with carbon with a double bond. So with carbon with a double bond, it's a lot like CO2. That CO2 is automatically nonpolar because it is symmetrical. So this one is nonpolar. So if this one is nonpolar, that one ends up a dispersion force. You can also do the difference there, but if the difference became polar, you'd get the wrong answer. So you have to make sure it's not symmetrical all the way around your central atom. That one is symmetrical because it's two double bonds, so that one is a dispersion force. So when you look at these, we're going to have to go back to our electronegativity values, figure out polar, nonpolar, or hydrogen. Hydrogen and fluorine, hydrogen and oxygen, or hydrogen and nitrogen. And then figure out polar, nonpolar to figure out if it's dipole-dipole or dispersion. The hydrogen bonds are usually the easier ones to figure out because you're looking for hydrogen and oxygen, hydrogen and fluorine, or hydrogen and nitrogen in the same compound. If you guys have any questions, ask. Otherwise, that is all of the notes for this part of the unit. Have a good day.